Mortys? Time to get swifty with Rotational Rick, because I'm here to talk to you about AP questions involving applications of integration. There's a question: what do you get when you divide the circumference of a jack-o'-lantern by its diameter? Pumpkin pie! And that's the way the news goes.
Now question 1 says let R be the region in the first quadrant bounded by the graph of G, and let S be the region in the first quadrant between the graphs of F and G as shown in the figure below. The region in the first quadrant bounded by the graph of F and the coordinate axes has area 12.142. The function G is given by g of x is equal to the square root of x plus 6 times cosine of pi x over 8. And the function F is not explicitly given. The graphs of F and G intersect at the point 4, 0. So this question has 3 parts. Let's do each part individually. First, we want to find the area of S. So if we're looking at our graph over here, S would be this region bounded by the y-axis and the functions y is equal to f of x and y is equal to g of x. So how do we find the area of a region between two curves? Well, all you have to do is set up a definite integral from a to b of your upper function minus your lower function. So in order to set up our definite integral, the first thing we need to figure out, what is our interval that we're going to integrate on? Well, we said this region is bounded by the y-axis, or x is equal to 0, so we're going to start at x is equal to 0. Then it's going to go all the way until these two functions intersect, which would be at x is equal to 4. So we're going to integrate on the interval from x is equal to 0 to x is equal to 4. It's nice that they give us a graph to help us figure that out. Next, which function is greater on that given interval? Well, we already know from this figure we see that f of x is greater than or equal to g of x on the interval from x is equal to 0 to x is equal to 4. So all we have to do then is set up our definite integral. Our definite integral is going to go from x is equal to 0 to x is equal to 4. And we're integrating the difference between f of x and g of x. So the integral from 0 to 4 of f of x minus g of x dx. Now to evaluate this, what we're going to have to do is we're going to have to integrate each term separately. The reason is because they don't give us the function f of x. They tell us what g of x is equal to, but they don't tell us what f of x is equal to. So we can't just find the antiderivative and use the fundamental theorem of calculus to evaluate it. Instead, we have to integrate each term separately like we do over here. Now we do this because the integral from 0 to 4 of f of x dx would be the areas of both regions here, S and R, added together. It would be this whole region underneath our function f of x and between our coordinate axes. Well, is there a way we can figure out what this is equal to? Well, if you look at the question, it says the region in the first quadrant bounded by the graph of f and the coordinate axes has an area of 12.142. So all we have to do is just recognize that the integral from 0 to 4 of f of x dx is that area that they're talking about. So we can take 12.142 and plug it in for the integral from 0 to 4 of f of x dx. But what about the integral from 0 to 4 of g of x dx? Well, to evaluate this, what we're going to have to do is we're going to have to take whatever function g of x is equal to, which would be the square root of x plus 6 times cosine of pi x over 8, and plug that in for g of x. Now this expression right here will get you the exact area of the region S right here. So how do we evaluate this? Well, as you can see, this question appeared on the calculator portion of the AP test. So all you have to do is enter this expression here into your calculator. You enter the number, then subtract the integral from 0 to 4 of this function right here. Make sure you put dx at the end, press enter, you can get that the area of the region S right here is approximately equal to 5.204. Remember to round to 3 decimal places on the AP test. That's what they require. Now part B says a solid is generated when S is revolved about the horizontal line y is equal to 5. Write, but do not evaluate, an expression involving one or more integrals that gives the volume of the solid. So this question just wants us to write a definite integral that will give us the volume of the solid generated by revolving the area of this region S right here about this horizontal line, y is equal to 5. So the first thing you should recognize in this question is that we are revolving a region about a horizontal line. Meaning, if we want to find the volume or set up an integral to find the volume, we need to figure out, are we using the disk or the washer method? Well, is your region fully connected to or fully adjacent to your axis of revolution along your given interval? No, it's not. There's going to be an outer radius and an inner radius. Meaning, when you revolve this region about your horizontal line, your cross sections are going to be washers. So you're going to have to use the washer method here. So let's go ahead and set up our washer method integral. The first step in setting up a definite integral would be to figure out what interval are we integrating on. Well, because this region is being revolved about a horizontal line, we know we are integrating with respect to x, so our interval is going to be in terms of x. And we see that our region S right here, bounded by the coordinate axes, goes from x is equal to 0 to x is equal to 4. So that's going to be the interval that we're going to integrate on. Now, typically, to find the volume of a three-dimensional figure, what we do is we integrate the area formula for the given cross-section. So if we were to revolve this region S about that horizontal line, y is equal to 5, we create a three-dimensional solid that has cross-sections that are washers. That's why we're using the washer method. So in the washer method, we have an outer radius and an inner radius, and we need to find both of those here. The outer radius, or capital R of x, is the distance from your axis of revolution to the function that is farthest away from that axis of revolution. In this case, that would be this function right here, g of x. So what is the distance between our axis of revolution and g of x? Well, we take whatever is greater and subtract whatever is lesser. In this case, our axis of revolution is greater than our function g of x. So in order to find the distance between these two, we would take our axis of revolution, 5, and subtract our function, g of x. That would give us. Now we need to find our inner radius. So our inner radius, or lowercase r of x, is going to be the distance from our axis of revolution to the function that is closest to the axis of revolution, which in this case would be f of x, this function. So how do we find this distance right here? Well, we take whatever is greater and subtract whatever is lesser. In this case, our axis of revolution is greater than our function, f of x. So to get this distance for our inner radius, we just take our axis of revolution, 5, and subtract our function, f of x. Now all we need to do is set up our definite integral for the washer method. Remember, the washer method is going to be pi times the integral from a to b of our outer radius squared minus our inner radius squared. So in this case, our interval goes from 0 to 4, so that's going to be our a and b. Our outer radius is 5 minus g of x. Our inner radius is 5 minus f of x. Now the best part of this question is this little aspect right here where it says write but do not evaluate an expression involving one or more integrals. So we wrote the definite integral that would give us the volume of the solid created by revolving region S about the horizontal line y is equal to 5. So all we have to do is box this up and call it a day. You're done. Now part C says region R is the base of an art sculpture. At all points in R, at a distance x from the y-axis, the height of the sculpture is given by h of x is equal to 4 minus x. Find the volume of the art sculpture. So this question is just testing your knowledge on, do you know how to find the volume of a three-dimensional solid using integration, using a definite integral? And the answer is yes, we know how to do that. To find the volume of a three-dimensional solid using integration, what we're going to do is we're going to integrate the area formula for the cross-section of that three-dimensional solid. So the first step in setting up this definite integral in order to find the volume is to figure out what interval are we going to integrate on. Well, it says the region R is the base of an art sculpture. So this region R is bounded by our coordinate axes. And in terms of x, it begins at x is equal to 0 and ends at x is equal to 4. So that would be the interval on which we're going to integrate. Next, we need to set up our definite integral and integrate the area formula for our given cross section. So remember, to find the volume, it's just the integral from a to b of the area of our cross section times dx. So what is the area of our cross section? Well, in this problem, it gives us information about the base and the height of this given art sculpture. The region R would be the base of the art sculpture, meaning that the base is going to be your function g of x on the interval from x is equal to 0 to x is equal to 4. Cool. So we have g of x is going to be our base. What is our height? Well, it says the height of the art sculpture is given by h of x is equal to 4 minus x, meaning in order to find the volume of this art sculpture, we're going to set up a definite integral from 0 to 4 of the area of a cross section, which would be base times height, or g of x times h of x. And we know what each of those functions are equal to. G of x is the square root of x plus 6 times cosine of pi x over 8. H of x is 4 minus x, so we can plug in each of those. Now, from here, because this question appeared on the calculator portion of the AP test, all you need to do is plug this into your calculator and evaluate the integral that way. So you plug this in your calculator, round to 3 decimal places, and you get the volume of the art sculpture is approximately 17.243. Now question 2 says let f and g be the functions defined by f of x is equal to 1 plus x plus e to the x squared minus 2x, and g of x equal x to the 4th minus 6.5x squared plus 6x plus 2. Let R and S be the two regions enclosed by the graph of f and g shown in the figure below. Now this has 3 parts just like the one before, so we're going to take each part individually. The first part says find the sum of the areas of regions R and S. So if we look at our figure, R and S would be the regions between these two functions. And look, there's area between the two functions on two separate intervals. On the interval from x is equal to 0 to x is equal to whatever x value this is. And then from x is equal to whatever x value this is to x is equal to 2. And it looks like on this given interval, our function g of x is greater than our function f of x. But then on this interval, our function f of x is greater than our function g of x. So we're going to have to set up two separate definite integrals to find the areas of each of these regions and then add those together. So the first step in setting up definite integrals would be to figure out what intervals are we working with. What are going to be the intervals of our given definite integrals? Well, we need to figure out where do these two functions intersect? Where do they equal one another? Well, the graph helps us out with two of those x values. They intersect at x is equal to 0 and x is equal to 2. But we need to find this third intersection point right here. So how do we do that? Well, that's where this calculator comes in. So what you're going to do is you're going to press the y equals button in your calculator and enter in both of these functions. Then you're going to press the second button and then hit calc, which is the trace button. And then scroll down to 5 where it says intersect. Once you do that, you're going to look at the graph and you're going to scroll close to where that intersection point is right here. Once you get there, you're going to press enter 3 times and that will tell you the x value at which they intersect, which is x is equal to 1.0328319. Now, since that is the intersection point, we know our intervals are going to go from x is equal to 0 to x is equal to that x value, and then from x is equal to that x value to x is equal to 2. So now that we have our intervals, we can go about setting up our definite integrals. And to do that, we need to figure out which function is greater on which interval. Well, that's what our graph is for. We see that on our first interval from x is equal to 0 to x is equal to this x value, g of x is actually greater than f of x. But on this interval from x is equal to this x value to x is equal to 2, we see that f of x is actually greater than g of x. So what that means in terms of this problem is that we're going to set up those two separate definite integrals. And in our first definite integral, the integral is going to be from x is equal to 0 to x is equal to this x value. And it's going to be of your upper function, which in this case is g of x, minus your lower function, which in this case is f of x. And then we're going to add that to the next integral, the second integral, which is going to be the integral from x is equal to this x value to x is equal to 2. And that's going to be the integral of our upper function, which now is f of x, minus our lower function, which now is g of x. Then all we have to do is just plug in what each of those functions are equal to for f of x and g of x. And now we are thankful that this question appears on the calculator portion of the AP test, because this would be a nightmare to try to do by hand. What we're going to do is we're going to plug all of this into our calculator using math 9, which is the integral function. We plug in each of these integrals separately. We add them together. We press equals or enter, and we get that the sum of the areas of these two regions would be approximately equal to 2.004. Again, rounding to 3 decimal places because that's what it requires on the AP test. Now, one thing I want you to note is that instead of plugging all of this into your calculator each time, what you could actually do is, because you plugged these in earlier when we were graphing them, you could use that to help you plug this in. And let me show you how that works. So we want to plug in the integral from 0 to this x value of g of x minus f of x. Now remember, when we graph this, you press the y equals button and you plugged in each of these functions already. So g of x is technically saved in your calculator as y sub 2. F of x is technically saved in your calculator as y sub 1. So what we could do to evaluate each of these definite integrals is just set up your definite integral like you normally do. Press the math button, then scroll down to 9, the integral function. Press enter, then enter your lower and upper limits of integration. But instead of plugging in g of x, this whole function up here, what you can do instead is press the vars button, V-A-R-S, it's the variables button. Then scroll over to y variables, and then scroll down to whichever one you want. Remember, we entered in f of x for y sub 1 and g of x for y sub 2. So we can plug in each of those to their respective spots in both of these definite integrals. Plug all of that in your calculator. Remember, there's another definite integral after this. Press enter and you get the exact same thing. It's just an alternative way to plug it into your calculator rather than having to re-plug in each of these functions. Now part B says region S is the base of a solid whose cross-sections perpendicular to the x-axis are squares. Find the volume of the solid. So this question wants us to find the volume of a three-dimensional solid with a known cross-section. They're squares. To find the volume of a solid with a known cross-section, integrate the area formula of that given cross-section. So we're going to set up a definite integral of the area of a square formula, which is just one of the sides squared. So the first step in setting up a definite integral would be to figure out what interval are we going to integrate on. What is our lower and upper limit of integration? Well, looking at our graph, we see that the region S goes from x is equal to this x value to x is equal to 2. So that's the interval on which we're going to integrate. Next, we need to figure out what is the area formula for the given cross-section here. Well, again, these cross-sections are squares. So the area formula for a square would just be the length of one of the sides squared. And the squares are perpendicular to the x-axis, meaning that the length of the base of your square is going to be the distance from this function to this function. So we just need to figure out what is the distance from this function to this function. Oh, that's easy. That's just this function minus this function. So on this given interval, which function was greater than which function? I forget. Well, if I look back at part A, I remember we found that on this interval, f of x was actually greater than or equal to g of x, meaning that in order to get the length of one of the sides of our squares, which would be the distance between these two functions, all I have to do is just take f of x and subtract g of x. So let's go ahead and set up our definite integral to find this volume. Remember, the volume of a three-dimensional solid with known cross-sections is just going to be the integral from a to b of the area of your given cross-section formula. And we said our cross-sections were squares, so the area of a square formula is just the length of one of the sides squared. And we just found that the length of one of the sides is the distance from f of x to g of x, or f of x minus g of x. If we square that quantity, we end up getting the area of our cross-section, which, if we then integrate on that given interval, will give us the volume of that solid. So now all we have to do is just plug in what we know f of x and g of x to be equal to, or you could use the vars button like we did last time, evaluate this definite integral, and we end up getting that the volume of the solid whose base is this region S and whose cross-sections perpendicular to the x-axis are squares is approximately equal to 1.283. Again, rounded to 3 decimal places. Now part C says let h be the vertical distance between the graphs of f and g in region S. Find the rate at which h changes with respect to x when x is equal to 1.8. So this question just requires a little bit of reasoning, and it's actually pretty easy. It says let h be the vertical distance between the graphs of f and g in region S. Well, we just figured out what that distance was, right? The distance between f and g in this region would be f of x minus g of x. So h of x is going to be equal to f of x minus g of x. Now, this wants us to find the rate at which h changes with respect to x, meaning it wants us to find the derivative of h with respect to x, or h prime of x. So if I were to take the derivative of this right here, the derivative of h of x is h prime of x. The derivative over here, I take the derivative of each term individually. The derivative of f of x is just f prime of x. The derivative of g of x is just g prime of x. Now we just need to answer the question, which says find the rate at which h changes with respect to x when x is equal to 1.8. So all we have to do is find h prime of 1.8, meaning we take 1.8, plug it in for x in the derivative of our function f, and then subtract when we take 1.8 and plug it in for x in the derivative of our function g. And remember, you just plug all of this into your calculator, press enter, and you end up getting that h prime of 1.8 is approximately equal to negative 3.812. Now, just to be sure, I want to make sure you know how to enter this in your calculator. You need to press the math button and scroll down to 8, which is the derivative function. Then make sure you are taking the derivative with respect to x, enter your function, or use the variable that corresponds with that. Then at the end, put 1.8 because we're evaluating the derivative of f of x at 1.8. Then subtract, and then repeat the process for g of x, or y sub 2. Press enter, and that should give you the rate at which h changes with respect to x at x is equal to 1.8. Now question 3 says let R be the region enclosed by the graph of f of x is equal to x to the fourth minus 2.3x cubed plus 4 and the horizontal line y is equal to 4 as shown in the figure below. So we again have 3 parts to this question. Let's take each part individually. First, it says find the volume of the solid generated when R is rotated about the horizontal line y is equal to negative 2. So the first thing you should recognize in this question is that we are revolving a region about a horizontal line. Meaning, if we want to find the volume or set up an integral to find the volume, we need to figure out, are we using the disk or the washer method? Well, is your region fully connected to or fully adjacent to your axis of revolution along your given interval? No, it's not. There's going to be an outer radius and an inner radius. Meaning, when you revolve this region about your horizontal line, your cross sections are going to be washers. So you're going to have to use the washer method here. So let's go ahead and set up our washer method integral. So the first step in setting up a definite integral to find the volume is figuring out the interval on which we're going to integrate on. Now, because we're revolving this about a horizontal line, we want to integrate with respect to x. So our interval will be in terms of x. Meaning, where does this function right here, f of x, intersect the line y is equal to 4? Well, it looks like at x is equal to 0, the two functions intersect one another. And then we have another intersection intersection point over here. So how do we determine what that is? Well, to determine this intersection point, we're going to have to do the same thing we did last time, where in our calculator, we enter the function f of x is equal to x to the fourth minus 2.3x cubed plus 4, and then we enter the function y is equal to 4. So we have both of those functions in our calculator. Then we press second and then calc, which is the trace button. Scroll down to intersect, which is 5, and then press enter. Then we'll scroll over close to that intersection point, press enter 3 times, and it'll tell us that point of intersection. And it looks like those two functions intersect at x is equal to 2.3. So our interval on which we're going to integrate on would be from x is equal to 0 to x is equal to 2.3. Now that we have our interval, we just need to figure out how do we set up the washer method. Well, to set up the washer method, remember we have two separate radii. We have our outer radius and we have our inner radius, and we need to figure out what each of those are equal to. The outer radius is going to be the distance from your axis of revolution to whichever function is farthest away from your axis of revolution, which in this case would be y is equal to 4. So to find that outer radius, we're just going to subtract whatever's greater from whatever's lesser. In this case, our function is greater than our axis of revolution, so we take 4, subtract -2, and we end up getting that our outer radius is actually going to be 6. Next, we need to find our inner radius, which is the distance from our axis of revolution to our innermost function, or the closest function, which in this case would be f of x. So to find our inner radius, we just take whatever's greater, subtract whatever's lesser. On this interval, f of x is greater than our axis of revolution, so I take f of x and subtract -2, and I end up getting f of x plus 2. That is going to be my inner radius. So now that I've found both my outer radius and my inner radius, and the interval on which we're going to integrate, I can set up my definite integral. And remember, the definite integral associated with the washer formula would be pi times the integral from a to b of our outer radius squared minus our inner radius squared. So all we have to do is take what our outer radius is equal to, which is 6, plug that in for capital R of x, then take what our inner radius is equal to, which is f of x plus 2, plug that in for lowercase r of x. Notice that I substituted in x to the fourth minus 2.3x cubed plus 4 for f of x here. I then can evaluate this definite integral using my calculator, because this question appeared on the calculator portion of the AP test. So all I have to do is plug this in your calculator like we have been doing. Remember to press math and then go down to the integral function 9, press enter, then enter all of this in. Make sure you put that pi out front, and you get that the volume of the solid generated is approximately equal to 98.868, again rounding to 3 decimal places. Part B says region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is an isosceles right triangle with a leg in R. Find the volume of the solid. So in order to find the volume of a solid with known cross-sections, in this case isosceles right triangles, all you have to do is set up a definite integral of the area formula for that given cross-section. So that's what we're going to do here. The first step in setting up a definite integral would be figuring out what interval are we going to integrate on. Well, since the region R is the base of our solid, we're clearly going to integrate from the beginning of R to the end of R. So x is equal to 0 to x is equal to 2.3. The next step would be to figure out what is the area formula for our given cross-section. If you recall, the area of an isosceles right triangle would just be 1/2 base times height. But because it's an isosceles right triangle, the base and the height are the exact same measurement. So it'd just be 1/2 base squared. So all we have to do is just figure out what is the length of our base, or the length of a leg of our right triangle. Well, because these cross-sections are perpendicular to the x-axis, all we have to do to figure out the length of one of our legs would be to figure out which of these functions is greater on this given interval. Well, we see that y is equal to 4 is clearly greater than f of x on this given interval from x is equal to 0 to x is equal to 2.3. With that knowledge, we can then set up our definite integral from a to b of the area formula for our given cross-section. And we know our a value is 0, our b value is 2.3. The area of our given cross-section would just be 1/2 base times height. But because it's an isosceles right triangle, the base and the height are the exact same measurement. So it'd just be 1/2 base squared. And the length of the base we determined from our figure over here would be the distance from y is equal to 4 to f of x. So that distance is just 4 minus f of x. Now we have set up an integral that, when evaluated, will give us the volume of this solid. So all we have to do then is evaluate this. We're going to take what f of x is equal to, plug that in here, and then all you have to do is plug this in your calculator, because this question appeared on the calculator portion of the AP test. So using the integral function in your calculator by pressing math and then 9, which is the integral function, you then enter all of this in, press enter, and you get that the volume of your solid is approximately equal to 3.574, again rounding to 3 decimal places. Part C says the vertical line x is equal to k divides R into two regions with equal areas. Write but do not solve an equation involving the integral expression whose solution gives you the value of k. So in this question, they're inserting a vertical line x is equal to k somewhere in region R. And it's going to divide region R into two regions with equal areas. And what we're tasked with doing is writing but not solving an equation involving integral expressions whose solution gives the value of k. So how would we write an integral expression involving the areas of each of these equal regions? Well, I know that the area of this region right here would be the integral from x is equal to 0 to x is equal to k of this upper function, which would be 4, minus our lower function, which in this case would be f of x. I know that to find the area of this region right here, I would set up an integral from k to 2.3 of our upper function, which is 4, minus our lower function, which is f of x. And since the areas of each of these regions are equal to one another, I could just set those two integrals equal to one another. And the cool thing about this is that your question says, write but do not solve an equation involving integral expressions. And that's exactly what this is. This is an equation involving integral expressions where if you were to evaluate this, you could solve for k. So we're done. That's all you have to do in this question. Now question 4 says let f of x equal 2x squared minus 6x plus 4 and g of x equal 4 cosine of 1/4 pi x. Let R be the region bounded by the graphs of f and g as shown in the figure below. So there's three parts here. The first part says find the area of the region R. So in order to find the area of the region R, notice that region R is between two curves. So I need to find the area of the region between two curves, meaning I'm going to set up a definite integral of my upper function minus my lower function. So the first question is, in setting up a definite integral, what is the interval on which we're going to integrate? Well, looking at this figure here, we see that our region R goes from x is equal to 0 to x is equal to 2. Next, we said to find the area of this region between two curves, we have to set up an integral where it's the upper function minus the lower function. So we need to figure out which function is greater on this given interval. Well, based on these graphs, we see that g of x, our function involving cosine, is actually going to be greater than f of x, our function that's just a quadratic function. If you're not sure which function is which, you can always just plug in some x value on this given interval, like 1 to each of these functions, and see which gives you a greater y value. But we do in fact see that g of x is greater than f of x on this interval. Now what we have to do to find the area between these two curves is just set up that definite integral from x is equal to 0 to x is equal to 2 of our upper function, which in this case is g of x, minus our lower function, which in this case is f of x. We plug in what each of those functions are equal to, and since this question appeared on the non-calculator portion of the AP test, you actually need to evaluate this. So to evaluate this integral, we need to prepare it for integration. So we're actually going to integrate each of these functions separately. In this function here, we can take this 4, which is just a constant, move it out front of the integral sign. Please do not move the 1/4 out front because you're taking the cosine of 1/4 pi x. You can't move that out front. Over here, we actually have a 2 that we can factor out from each of these terms, which we can take out front of our integral sign, and we're now prepared for integration. So let's go ahead and integrate each of these and use the fundamental theorem of calculus to evaluate the definite integrals. So to integrate here, what you need to do is take the antiderivative of each of these terms in here. So over here, to take the antiderivative of the cosine of 1/4 pi x, notice that it's not just cosine of x, it's cosine of 1/4 pi x. To integrate here, you need to use u substitution. You're going to have to set u equal to 1/4 pi x. That means when you take the derivative of this with respect to x, you get du dx is equal to 1/4 pi. Multiply both sides by dx, you get du is equal to 1/4 pi dx. Now because you're already plugging in u for the 1/4 pi x in here, there is no other 1/4 pi. So we actually have to take that and move it to the other side of this equation here. So we're going to multiply both sides by 4, divide both sides by pi. We get 4 over pi du is equal to dx. So again, I can substitute u in for the 1/4 pi x. Then I'm going to substitute 4 over pi du for the dx. Now because this is a definite integral and I'm using u substitution, I need to rewrite my limits of integration. So I'm going to take 0, my lower limit of integration, and plug it in for x in whatever I set u equal to. So when I simplify over here, 0 times pi times 1/4 is still 0. So my new lower limit of integration is still 0. Then I'm going to take my upper limit of integration, 2, plug that in for x in whatever I set u equal to. And I simplify this, I end up getting pi over 2. So that'll be my new upper limit of integration here. Now this 4 over pi is just a constant. I can move that out front, multiply it with the 4 that's already there. I get 16 over pi. Now I'm actually ready to integrate. So I take the antiderivative of cosine of u du, which is just sine of u. Over here, when I take the antiderivative of x squared minus 3x plus 2, I take the antiderivative of each term separately. And now I use the fundamental theorem of calculus on each of these. Over here, I take my upper limit of integration, pi over 2, plug it in for u, and subtract when I plug in my lower limit of integration, 0 for u. Over here, I take my upper limit of integration, 2, plug it in for each of the x's. Subtract when I plug in my lower limit of integration, 0 for each of the x's. I then simplify each of these parameters parentheses and multiply that 16 over pi out front here, multiply that 2 out front here, and I get 16 over pi minus 4/3. That's the most we're going to simplify this because, again, this is on the non-calculator portion of the AP test. So we have found the area between those two curves on that given interval. Part B says write but do not evaluate an integral expression that gives you the volume of the solid generated when r is rotated about the horizontal line y is equal to 4. So in this question, we are taking this region r and revolving it about the horizontal line y is equal to 4. Now, anytime you see revolving about a horizontal line or a vertical line, you're likely going to deal with disk method or washer method. So the question is, which is it in this case? Well, is your region fully connected to or adjacent to your axis of revolution along your given interval? No, there's a space in here, right? Because of that, when you revolve this region about your horizontal line, your cross sections are going to be washers. So you're going to have to use the washer method here. So let's go ahead and set up our washer method integral. The first step is to figure out what interval are we integrating on. Well, as you can see from our graph over here, because we're revolving about a horizontal line, we know we're integrating with respect to x. So our interval should be in terms of x. And the region r goes from x is equal to 0 to x is equal to 2. So that's the interval we're going to integrate on. Next, we need to determine, because we're using washer method, which is our outer radius and which is our inner radius. So our outer radius is going to be the distance from our axis of revolution to whichever function is farthest away from our axis of revolution, which in this case would be this function right here, f of x. So how do I find this distance? I take whatever's greater, subtract whatever's lesser. So in this case, our axis of revolution is actually greater than our function on this interval. So we take 4, subtract f of x, and that should give us the length of our outer radius. Our inner radius is the distance from our axis of revolution to our inner function, which in this case would be g of x. So to find this distance right here, we take whatever's greater, subtract whatever's lesser. So in this case, our axis of revolution is actually greater than our function again. So we're going to take 4, subtract g of x, and that'll give us the length of our inner radius. So now we plug in what we know to the washer method, which is pi times the integral from a to b of our outer radius squared minus our inner radius squared. We're going to plug in 0 for our a. We're going to plug in 2 for our b. We plug in 4 minus f of x for our outer radius, 4 minus g of x for our inner radius. Now the best part about this question is that it says write but do not evaluate. So we did. Perfect. We wrote an integral expression that gives you the volume of the solid generated when r is rotated about the horizontal line y is equal to 4. Now part C says the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a semicircle. Write but do not evaluate an integral expression that gives you the volume of the solid. So we again are finding the volume of a solid. This time we have known cross-sections. They are semicircles that are perpendicular to the x-axis. So to find the volume of a solid, if we know what the cross-sections are, we just integrate on our given interval the area of the cross-section formula. So let's go ahead and set up our integral. Remember, the first step in setting up our integral is determining what interval are we integrating on. In this case, because our cross sections are perpendicular to the x-axis, we're going to integrate with respect to x. So our interval is going to go from x is equal to 0, the beginning of our region R, to x is equal to 2, the end of our region R. So remember, to find the volume of a solid with known cross sections, it's just the integral from a to b of the area of your given cross section formula. Next, we need to determine what is the area of our given cross section formula. Well, these are semicircles. So the area of a semicircle is just 1/2 pi r squared. So all we have to do is just figure out what is our radius in this case. Well, remember, these semicircles are perpendicular to the x-axis and they're popping up from the page. Because of that, the distance from our upper function here, g of x, to our lower function down here, f of x, that is going to be the diameter of each semicircle, meaning the radius of each semicircle would be half that distance. So the distance from this function up here to this function down here we know is g of x minus f of x, and half of that distance would then be 1/2 the quantity g of x minus f of x. So that will be the radius of our given semicircles. Now we could simplify this a little bit further by taking this 1/2 pi, moving that out front because those are both constants, and just making it pi over 2. And then before you try to do too much here by starting to integrate this, look at the question. It says write but do not evaluate an integral expression that gives you the volume of the solid, which we just did. We wrote an integral expression that gives you the volume of the solid whose base is this region R and has cross sections that are semicircles that are perpendicular to the x-axis.